So implicit differentiation. Implicit differentiation is just a method that we can use to differentiate some equation, some relation that is not a single function of x. So we'll remember that what we do is we differentiate both sides of the equation with respect to x, and any terms that you differentiate that have a y in them end up with a dy dx, because you're taking the derivative with respect to x of a y term, gives you a dy dx using the chain rule, and then you just factor out and solve for the dy dx. Should be easy. These are your steps. If you need to look at the steps sometime, there they are. It's wonderful. We'll start with a really easy one. Y squared equals x. So first, get the derivative with respect to x of both sides. On the right-hand side, what's the derivative of x with respect to x?
One.
Yeah, and the derivative of y squared with respect to x, we'll first take the derivative of y squared with respect to y, which is 2y, and multiply it by the derivative of y with respect to x, dy dx. We're looking for dy dx, so just divide by 2y. Easy enough?
Uh-huh.
Great. Let's do another one. We want to take the derivative with respect to x of both sides. And the left side, oh, we just did that one. What should that one be?
2y dy dx.
2y dy dx. That's great. And on the right-hand side? Should have. Go ahead, x plus 1 times 1 minus.
X minus 1 times 1.
All right, over x
Plus 1.
squared. And if we distribute all this junk out on the numerator and distribute the minus sign, the x and the minus x will go away. And we have a 1 minus a negative 1, so that's a 2. So we got to get dy dx equals 2 over 2y times x plus 1 squared. When we bring the 2y to the left, or from the left to the right, cancel out the y's, 1 over y times, or sorry, cancel out the 2's, 1 over y times x plus 1 squared. Easy enough?
Oh, yeah.
Wonderful. All right. Let's do this slightly more complicated one together, and then I'll let you guys do one or two on your own to make sure you're still able to do this without my expert guidance. So we have x squared y plus xy squared equals 6. We're going to take the derivative with respect to x of both sides. On the right-hand side, that's very easy. We should get 0. But on the left-hand side, we have x squared y. X squared y is a product of two functions, so we have to use the product rule. So x squared, derivative of y, plus, I'm right over here because I feel like I'm going to run out of room, plus y, and then derivative of x squared, which is 2xy. Then we have xy squared, which is also the product rule. So that ought to be x. And then the derivative of y squared, which will be 2y dy dx. And then derivative of x is 1 times y squared. Everybody good with all of that?
Yes.
Cool. Now we'll take our 2xy and our y squared to the other side. And over here, we've got now dy dx times x squared plus 2xy. And we'll divide by the x squared plus 2xy. So dy dx equals negative 2xy minus y squared over x squared plus 2xy. Good or no? Good.
Good.
All right. All right. This one's an easy one. We'll do this one together too because it's so easy. X equals tangent y. On the left-hand side, what do we get?
1.
1.
1. And on the right-hand side, what do we get?
Secant squared. Oh, go for it. Sorry.
All right. While you guys are trying to figure out who's going to say it, I'm just going to write it. Secant squared y dy dx. Yeah? And divide by the secant squared. And we could rewrite that as, instead of 1 over secant squared, how about just cosine squared y? And we'll note that the big difference between these and all the other derivatives we've done is that these ones can end up with a y in your final derivative, rather than before, they sort of all ended up with just x's, right? Yeah. And we, this is actually the method that we would use to find the derivatives of all the inverse trig functions, right? Because, you know, if we have something like y equals the inverse tangent of x, well, that tells us that tangent x is equal to y, and then you can go through and solve it. All right, you guys do this one. Ready, go.
I think.
All right, so 2x plus 2y dy dx equals 0. And subtract the 2x and divide by the 2y gives us negative 2x over 2y, or just negative x over y. And if we're looking to evaluate that, right, the vertical bar is evaluating it at the point 3, negative 4. That gives us negative 3 over negative 4, or 3/4. Good?
Yes.
Yep.
Right. All right, you guys do this one. Ready, go. I think that was a yes that you were done. So what do we got? On the left-hand side, 2 dy dx. And on the right, 2x plus cosine y dy dx, which gives us what? Subtract the cosine y over, so we got 2 minus cosine y times the dy dx is equal to 2x, or dy dx is equal to 2x over 2 minus cosine y. And so why is this defined at every point? Well, for any x value, we could plug that in, right, and get a number. The only thing that would make this undefined is if 2 minus cosine y were to equal 0, which would tell us that cosine y would equal 2. But we should know that cosine y cannot equal 2 because the cosine of any number is always between negative 1 and 1. Yeah? Good? Easy?
Good.
Spectacular. All right. Last one here. All right, you guys go through and find the derivative of this, and yeah, it'll be good. Yeah, just find me the derivative. I was going to make you find the equation of the tangent line at a point, but we'll worry about that another day. Go find me dy dx. Ready? Last one of these. Go. Should get 3x squared plus 3y squared dy dx. And then minus 9x times y. So I'm going to do this, I guess, as minus 9x is one function and y is the other. So I'll say minus 9x dy dx, and then minus 9y equals 0. And then all we gotta do is solve for our dy dx. So we'll put the 9y and the 3x squared over there. So we got 9y minus 3x squared. On the left-hand side, we can take out the dy dx as a 3y squared minus 9x. And that gives us 9y minus 3x squared over 3y squared minus 9x. Or if you simplify it down, 3y minus x squared over y squared minus 3x. All good? Everybody good with that?
Good.
Cool. Anybody have any issues with any of this implicit differentiation? Because if you can't do the implicit differentiation, you're going to really struggle with polar derivatives and parametric derivatives and all that stuff. They're sort of all interrelated a little bit. All right. Before we finish for the day, then we're going to really quickly talk about one last rule, which is the inverse rule. The inverse rule says that if we have two functions that are inverses of each other, and if two functions are inverses of each other and one has the point AB, then the other must have the point BA, that being part of the nature of inverse functions, right, is that you flip the x and the y values of any point on one and it should give you a point on the other one. So the rule tells us that if two functions are inverses of each other, then the derivative of the inverse function at A should be equal to the reciprocal of the other function at B. So if I'm going to say f and f inverse are inverses of each other, which they must be since it's f and f inverse, and f contains the point, I think I had typed this differently, f contains the point b comma a, and f inverse then would contain the point a comma b, then f inverse prime of a is 1 over f prime of b. Easy enough. Hopefully. All right, so if f of x is x cubed and g is the inverse of f, and we want to find a g prime of 8, what can we do? First off, g must contain a point 8 comma something, which tells us that f contains a point something comma 8. Everybody agree with that?
Yep.
Okay, so if we want g prime of 8, it ought to be 1 over f prime of whatever this value is. So we need to figure out what is that value right there. Okay. Well, we know that that value occurs when f of x equals 8. So that would be at an x value of 2, which makes both of these a 2, which tells us that g prime of 8 ought to equal 1 over f prime of 2. And f prime of x is 3x squared. And that makes f prime of 2 equal to 3 times 2 squared, 12. So g prime of 8 ought to equal 1 over 12. Good or no?
Good.
Was that a yes? I couldn't understand that.
Yeah, that was a good.
Oh, good. Haha, perfect. That's it. We're done.